Alrighty, let's have a quick look at using the mole equations. Number of moles is equal to the mass over the relative mass. This, I would say, would be your main one. Often we're given the mass of something with stoichiometry and asked to work out the mass of something else. So first we convert to a moles, look at the mole ratio. That tells us the moles of the second substance, and then we can convert that moles back to a mass. So great. This, I would say, would be the main one. There is, of course, this other one, number of moles is equal to the number of particles divided by Avogadro's number. Sometimes you won't be given the mass of a substance, you'll be given the number of molecules or number of atoms. So we'd use this one. Avogadro's number is, of course, 6.022 by 10 to the 23. It is a constant. That number doesn't change. It goes a little bit more accurate than that if you wanted to throw down some more decimals, but usually people take it as 6.022 by 10 to the 23. So these are your 2 mole equations. Actually, there is another one. Number of moles is equal to the concentration times the volume. This is dealing with solution stoichiometry. So when you're doing solutions work, you'll be using this one. This one's actually quite an obvious one. When you're talking about a solution, a concentration of a solution, let's say you have some acid. What's its concentration given as? Maybe 5 molar. Great. Well, what does that molar actually mean? It means 5 mole per litre. Well, a mole per litre, what is that? That is a number of moles per litre is your volume. Great. And what do we just work out? Well, that is the concentration. So there we go. Concentration is given in moles per litre. And if you just rearrange this, get rid of that V over there, put it over here, there you have a third mole equation, N equals CV. But anyway, like I said, that's for solution chemistry. We'll deal with that later. For now, let's work with moles equals mass over relative mass, and maybe a bit of moles equals number of particles over Avogadro's number. Here we have a pretty straightforward question. We're finding the mass. Well, your mole equation doesn't find the mass, does it? It finds the number of moles, which we don't need to find because we've been told that. But we can just rearrange this. We don't want mass divided by relative mass, so let's get rid of that. We'll dump it on the other side, and when you take it on the other side, it's been multiplied. So we can write that a little bit more cleanly. We know moles equals mass over relative mass, but that gives us that the mass is equal to the moles times the relative mass. Well, the number of moles is given to us here. It's 3.5. The relative mass of copper, well, that's where we go to our periodic table. And we find copper, and we find that its relative mass is 63.546. And so we can just multiply these and come out with 222.411 grams. Of course, it's a mass. We need to put our units. Let's make that decimal a bit clearer, not part of the 2. So there we go. The mass of 3.5 mole of copper is 222.411 grams. Lovely. Next equation. Let's scroll. Here we go. How many moles of CO2 in half a gram of CO2? And also, how many molecules is that we're talking about? Well, let's go to the number of moles first. Number of moles is equal to the mass over the relative mass. Mass is given to us, half a gram. So it's 0.5 divided by something. Well, that's divided by the relative mass of carbon dioxide. Now, what is carbon dioxide? Let's see, we have a carbon, we have 2 oxygens, so our relative mass is going to be the mass of a carbon. What have we got? 0107 plus, there are 2 oxygens, so 2 lots of 15.994. That's the relative mass of oxygen, but we have 2 of them added to the carbon. So that will give us a relative mass of 44.0095, but we don't actually have to go off to the side and work out what that relative mass is. We can just do it like I've done here, where we incorporate the finding of that relative mass into the equation to find the moles. Anyway, we now have 0.5 divided by 44.0095, and that will give us the number of moles of CO2 to be equal to 0.1136118338 mole. Okay, the symbol for mole is the mol, M-O-L. Now, we wouldn't leave our answer as that. You don't go giving that many decimal places. That would be crazy. Let's go to 3 decimal places, 0.114 mole. Now, when you round, you really should show your rounding. I've rounded to 3 decimal places, so I should say that I've rounded to 3 decimal places. So that's the answer to the first part. The first part was said, how many moles are there? Well, there are 0.114 mole of CO2 in that half gram sample. But then we're asked how many molecules are there. So now we're going to use the other mole equation. Right, so for how many molecules there are, we know that moles is equal to the number of things divided by Avogadro's number, 6.022 by 10 to the 23. Now we rearrange this equation to find the number of particles. Actually, also, it's a good idea to say what you're talking about, the number of CO2 molecules. Don't say N equals. Say N of this stuff equals, and we have the number of moles times Avogadro's number. Avogadro's number is just a number, and the number of moles, well, we calculated that in the previous question. Okay, so first we had to find the number of moles because we were asked to, but then that lets us calculate this next part where we needed that number of moles. However, remember how the answer was 0.114 mole for the first part? Yeah, what we're not going to do in this calculation is write 0.114 times Avogadro's number. Don't use a rounded answer in a further calculation. So for the number of moles, we are going to stick with 0.11361183338. Okay, so use the full accuracy that your calculator gave you in the first place. Don't use a rounded figure in a further calculation. Anyway, that number of moles has been multiplied by Avogadro's number, 6.022 by 10 to the 23. And that gives us a number of molecules of 6.841704632 by 10 to the 21. Well, I'm just going to go straight to my rounding, 6.842. What I said, by 10 to the 21 molecules. Now this has been rounded, so what do I need to do? I need to show my rounding. That is to 3 decimal places. 3 dp says 3 decimal places. And that was that question. But don't worry, we have another one. What is the mass of that many molecules of ammonia? Well, let's find out. Now, we've been given the number of molecules. First, we will have to, let's just scribble this down. We've got this, the number of molecules. First, we will have to change that to a number of moles, and then we can change that to a mass. So once again, in this question, we're going to use both of those, but the number of particles gets changed to moles first. So let's do that. The moles, remember, we should say what we're talking about, of ammonia. Number of moles of ammonia is equal to the number of things divided by Avogadro's number. It's always good to start with the equation and then rearrange the equation if you need to. Now, in this case, I don't need to rearrange that equation. It's going to find what I need to find, number of moles. So, number of particles, the question told us was 6.93 by 10 to the 22. that has been divided by 6.022 by 10 to the 23. That's Avogadro's number. And that, when we do the maths, comes out as 0.1150780472 mole. Right, that's the number of moles. A bit more than 0.1 of a mole. Now, if that was just the question, how many moles are there? Feel free to round it, 0.115 mole to 3 decimal places. But that is not the actual question. We want to turn that into a mass, and we're not going to use a rounded answer in a further calculation. So we'll just leave that for the moment as the entire decimal that the calculator gives us. And now that we know how many mole we have, we can work out the mass. So the mass of ammonia, remember moles equals mass over relative mass, so mass is equal to moles times relative mass. So we just bring that number of moles down, 0.11507800472, and we are multiplying this by the relative mass of ammonia. Well, for that we just go to our periodic table. We see nitrogen is 14.0067. We have 3 hydrogens, so add to that 3 lots of hydrogen, which is 1.00794. So this part here is finding our relative mass of ammonia. You could go off to the side and sort of work it out and just get the number in this case being 17.03052, but you don't really have to. You could just incorporate it into the calculation of finding the mass. So I've got number of moles, 0.115-ish, times the relative mass of ammonia, 17-ish, and we do that calculation, that multiplication, and we come out with 1.96 grams of ammonia. This is to 2 decimal places. If you wanted the whole answer, it's 1.959838984 grams. And you could write that whole thing down. By all means, write down the entire decimal answer and then round it. But because this is my final answer, the question, remember, asked, what is the mass of ammonia? Well, I've found the mass of ammonia. So that's my final answer. I can just go straight to my rounding and save myself, 5 to 10 seconds of writing out the whole decimal. All right, do we want to do one more? Here's one more. How many atoms are there in 40 grams of copper? Well, this is essentially just going backwards from the previous example, using both mole equations again, but starting with the mass and going to a number of particles, whereas the previous we started with the number of particles and went to a mass. So we may as well just do this one super quick. We're going to change this mass into a number of moles of copper. Once we know how many moles of copper, we can work out how many atoms of copper there are. So let's go straight to it. The mass, wait, no, not the mass, we're given the mass. We want to find the moles of copper. It's equal to mass over relative mass, which is 40 over what the periodic table tells us the mass of copper is, and that's 63.546. This gives us a number of moles of 0.629465269 mole. Cool, that's the number of moles. Now we can just convert that into a number of particles. Number of moles is equal to number of particles over Avogadro's number. Therefore, the number of particles, and let's say what we're talking about. We're talking about copper atoms, is equal to moles times Avogadro's number, which is equal to, well, the number of moles we've just calculated, 0.629465269 93 multiply this by Avogadro's number, 6.022 by 10 to the 23. And we're going to come out with the number of copper atoms of about 3.791. It's 3.790639851 by 10 to the 23, but I'm going straight to my rounding. 3.791 by 10 to the 23. We're talking about atoms of carbon. So that many atoms, but remember that has been rounded to 3dp. Show your rounding. So there we go. Just a quick look at using the mole equations. You will use them a lot when you do stoichiometry, and by a lot, I mean like seriously, a lot. Well, that's the video done. If you liked it, brilliant. Hit the like button and leave me a comment too. Now you know what to do. Go hit that subscribe button. We'll see you next time.